everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to be able to identify the acyl chloride and ester functional groups, and then to understand the reactions of acyl chlorides with water, alcohols, concentrated ammonia and amines, and then to understand hydrolysis reactions of esters in acidic and alkaline solution. Lastly, we're going to look at understanding how polyesters are formed by condensation polymerization reactions. So now we're going to look at esters. So esters have the functional group of COO and then two R groups, which aren't necessarily the same. And so they are made by reacting a carboxylic acid with an alcohol. And this reaction is called an esterification reaction, which basically means making an ester. And so how we name esters is that we use YL for the alcohol section and O8 for the carboxylic acid section. So for example, if we add together ethanol and methanoic acid, ethyl methanoate. And so what it looks like is we have ethanol, so that's CH3, COH, and we add it with methanoic acid, so we have HCOOH, and this forms. How you do it is you first look at, I like to look at the acid first, so I write down the bit of the acid before until I get to the oxygen. So I write this bit and then I stop when I get to this oxygen. And now what you do is you have a look at the alcohol you have and you flip it over. So imagine there's a mirror line here. And so you flip it over and what you get is that you have the two carbons and then the hydrogens attached. So you add it on to the carboxylic acid, but you're removing the hydrogen, also the oxygen. And this is because we're removing a water when we add them together. And so we form this, and we also form water. Now we're going to look at naming this. So what we do is we divide it up. So we have this section. And this section comes from the alcohol. So this is from the ethanol. And then we have this left-hand section. And this is from the acid, so from the methanoic acid. And so again, the rule is that we use YL for the alcohol section and O8 for the carboxylic acid section. And so what happens is that we have the alcohol section, so we have that the alcohol is equal to ethanol. And so this becomes ethyl because we're using the prefix of eth, and then we're using the suffix of YL. And then for the acid, so for the acid, we've got methanoic acid. And so we use methanoate. And again, we're using meth because it's the prefix for one carbon. And then we add O8 at the end. And so the whole name of the molecule that we get is ethyl methanoate. So we put the name of the alcohol first. And now we're going to look at a harder example. So this time we're adding 3-methyl-butanol and ethanoic acid to form something and water. So first drawing out 3-methyl-butanol, we have 4 carbons in the main chain, and then we have the OH. And then we have a methyl on the third carbon, so this one. Because the carbon of the OH gets priority, so it gets number 1. And then we have a hydrogen, another hydrogen, and hydrogens all the way round. and we're adding this with ethanoic acid. So ethanoic acid is 2 carbons, and so we have CH3, C double bond O, OH. And this will form if we again use the acid first. So we draw it out until we get to the oxygen. So C double bond O and then oxygen and then stop. And then now you look at the alcohol and flip it over and connect it, but getting rid of the OH. So we start with the C and then we have C. So we have 4 carbons and then the hydrogen. And then we have hydrogens on this last carbon. On the second last carbon, we have a methyl group and a hydrogen. And these are all hydrogens. So this is how we form it. And we also form water because we've taken out this hydrogen here and also this OH. So they react together to form water. And how we name this is, again, we divide it up. So we first look at the alcohol. So we have this section here, which comes from the alcohol. And then we have this section here. This comes from the acid. And so what we have is we have that the alcohol is 3-methyl butanol. And so what we get is 3-methyl butyl, because again we're using the suffix of YL. And then for the acid, we have ethanoic acid. And so we get ethanoate, because again we're using the suffix of 08. And so the whole name for this ester would be 3-methyl butyl ethanoate, because again we put the alcohol first, and so this would be its name. So now we're going to look at the hydrolysis of esters. So esters can be hydrolyzed in acid or alkaline conditions to form alcohols and carboxylic acids, or salts of carboxylic acids. So the first reaction that we're going to look at is hydrolysis of esters using water and a H+ catalyst. So for example, if we have this ester, CH3, C double bond O, and then OC2H5. So how we would name this is we would first name the alcohol. So we have ethanol, and then we have also ethanoic acid. So this is ethyl ethanoate. And if we add water, we get an equilibrium setup when we add a H+ catalyst. And we'd also have to have H+ catalyst to go the other way. And we reform the carboxylic acid and the alcohol. So we have ethanoic acid forming and also ethanol. And this reaction does not go to completion, and so produces a mixture of this ester, water, acid, and alcohol. And the reaction occurs because of the partially positive charge on the carbon, which is susceptible to nucleophilic attack by the water molecule. So what it is that there's a very large electronegativity difference between oxygen and carbon. So this carbon gets a partially positive charge. And this water, if you can remember, acts as a nucleophile. So we have water that looks like this, and we have 2 lone pairs of electrons on the oxygen. And so one of these pairs can form a covalent bond with this carbon. And so this is how we can form carboxylic acid and the alcohol. Now, if we look at hydrolyzing esters using a base, it's slightly different. So this time, if we again start with ethyl ethanoate. And then we add sodium hydroxide this time. What we form is, first of all, we don't have an equilibrium, we just have a straight reaction. And we form a carboxylate. And the ethanol forms as well. So what's happening here is the sodium hydroxide is acting as a base and it's hydrolyzing the ester, so splitting it up. And this reaction is a lot faster and it also goes to completion because the salt of the carboxylic acid is formed and this removes the carboxylic acid and so the equilibrium is not established. And this is also called saponification because we can make soap this way. So the salt that's created and this sodium ethanoate is actually a soap. So now we're going to talk about polyesters. And polyesters are a type of condensation polymer and they're formed from diols and dicarboxylic acids. And the reason why is that to form esters, we need an alcohol and a carboxylic acid. And so in order to get this ester group, C double bond O, to repeat over and over again, we need diols and dicarboxylic acids because then we have the two functional groups on either end of each of these chemicals. And so, for example, we can look at ethane 1,2-diol. So we have OH and then CH2OH. So we have an alcohol group on either end. So we call this ethane 1,2-diol. And we have benzene 1,4-dicarboxylic acid, which looks like this. And then we have a benzene, carbon double bond O, and then OH. So this is benzene 1,4-dicarboxylic acid. These two chemicals actually react to form terylene, which is a polyester. So what I'm going to do first is I'm just going to write them both out again. So we have HO, CH2, CH2OH added with HO and then C double bond O, which is attached to benzene, and then OH, then added with another one of these HO, CH2, CH2OH plus dot 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 plus dot dot dot. What we're doing is we're removing waters. So we're removing this water here. So this water comes out in the condensation polymerization. And this water also comes out as well. And so on down the line. And so the polymer we form is one that looks like this. So we have O, CH2, CH2, and that line is just to indicate that it goes on. And then we have O, C double bond O, and then the benzene, and then a carbon, and double bond oxygen, and then we have another oxygen, CH2, CH2O, and then dot dot dot. So again, we can say that. And so now you can see that we have these ester groups that are repeating. So this here is an ester group. And so is this one. And there'll be many more down the line. And this is why this is called a polyester. And we can actually work out the repeating unit of this because what we do is start here and then we just go along from left to right and see when we start to repeat ourselves. And you'll find that it's over here. And so the repeating unit for this ester, this polyester, sorry, is OCH2, CH2, O, C double bond O, and then a benzene, another carbon, and then a double bond O. And so this is our repeating unit for pterylene. So now we're going to talk about acyl chlorides. Acid chlorides or acyl chlorides are a form of acid derivative. And an acid derivative is a carbonyl containing functional group other than an aldehyde or a ketone. And these are made up from carboxylic acids. And these acyl chlorides have an OH group in its corresponding carboxylic acid replaced by a chlorine atom. And the way we name acyl chlorides is by using the suffix anoyl and chloride. So for example, we have ethanoyl chloride. First, because it starts with eth, then we know it's 2 carbons. So if we draw out the corresponding carboxylic acid, we have CH3, C double bond O, OH. So this is ethanoic acid. And acyl chlorides always have the OH group replaced by a chlorine atom. And so this means that ethanoyl chloride is CH3, C double bond O, and then instead of the OH, we have Cl. And so this is our ethanoyl chloride. And as another example, we could have CH3, CH2, CH2, C double bond O, Cl. And how we would name this is, again, you count up the carbons. So we have 1, 2, 3, 4 carbons. And so the name of this would be butanoyl chloride. Now we're going to have a look at the reactions of these acyl chlorides. So when acyl chlorides are reacted with water, alcohols, concentrated ammonia, or primary amines, we have acylation reactions. And the definition of an acylation reaction is just a reaction where we introduce the acyl group into a compound. And the acyl group is just R with C double bond O. So this is an acyl group. And acylation reactions are nucleophilic addition-elimination reactions. And this is because water, alcohols, concentrated ammonia, and amines, primary amines, all act as nucleophiles. And so we add the acyl group to these nucleophiles, and in the end, we also eliminate the chlorine atom, which was part of these acyl chlorides. And so first we'll look at water. So I'm going to look at ethanol chloride as an example. So we'll have ethanol chloride, which has a formula of CH3, C double bond O, and Cl. So this is ethanoyl chloride. And we're going to add it with water. So if I draw out a water molecule, we have an oxygen with 2 lone pairs of electrons and 2 hydrogens. And because the oxygen has 2 lone pairs of electrons, it acts as a nucleophile because a pair of these electrons can be donated to the carbon atom in this acyl chloride to form a covalent bond. And so we react it with water, and what we form is CH3, C double bond O, and then OH. And we also form HCl. And what we formed is ethanoic acid. From this ethanoyl chloride. Because what we've done is we've basically bonded the oxygen with the partially positive carbon. And so this is how we've removed the chlorine. And also one of the hydrogens off the water has also been removed. And this chlorine and the hydrogen react together to form HCl. And the HCl is actually, you'll actually see misty fumes from this HCl given off. And then now we're going to look at with alcohols. So again, I'm going to use ethanol chloride as the example. So we have CH3, C, double bond O, and then Cl. And this time we're adding an alcohol. So I'm going to draw another oxygen, and this time I'm going to have a hydrogen, and now I'm going to have an R group, which is just an alkyl group. And again, we have the 2 lone pairs of electrons on the oxygen, and so it can act as a nucleophile. And then what we form is CH3, C double bond O, and then OR. And again, we form the HCl gas. So this is again misty fumes. And what we formed is we formed an ester. And the ester depends on what our R group is. And we know that we can actually make esters from carboxylic acids and alcohols in the presence of a H+ catalyst. But this reaction is actually much better at making esters because the reaction is much quicker and it's not a reversible reaction. So thirdly, we're going to look at the reaction of acyl chlorides with concentrated ammonia. And again, we're going to use CH3CCl. So this ethanol chloride. And so we have ammonia, so we have nitrogen with 3 hydrogens attached. And nitrogen has one lone pair of electrons to form a covalent bond. So what we form is CH3, C double bond O, and then NH2. And also we have, again, this HCl gas, which gives off misty fumes. And what we formed is we formed an amide. And how we tell when we have an amide is when we have this C double bond O and NH2. So this is what an amide is. And because it's got 2 carbons, we call this ethanamide. So we can get propanamide if we have 3 carbons and butanamide if we have 4 carbons, etc. And again, this is with ethanol chloride. So again, what's happening is that the nitrogen, the 2 lone pairs, are moving towards the partially positive carbon of the ethanol chloride. And so it forms a covalent bond, which is this bond that we see here. And then because of that, the chlorine gets removed, and also one of the hydrogens off the nitrogen of the ammonia originally also gets removed. And another thing we actually need to know about this reaction with ammonia is that this HCl form can be reacted with another ammonia, and this forms NH4Cl. And this is really important to remember because actually 2 things happen in this reaction. And so the overall reaction is that ethanol chloride will react with 2 moles of this ammonia to form ethanamide and also this NH4Cl. So now we're going to look at primary amines. And we have, again, ethanol chloride. And we're going to react it with an amine, so a primary amine. So we're going to have an R group, a hydrogen and another hydrogen. And again, the nitrogen has a lone pair to donate to the carbon. And what we form is CH3, C double bond O, and then N, and then H, and then R. So again, we have the chlorine being substituted out by the nitrogen, so we form a bond between the carbon and the nitrogen, and then one of the hydrogens of the nitrogen will then be removed as well. And so again, we form HCl. And this molecule that we formed is actually what we call an N-substituted amide. So because for an amide, we would have had to have this R as a H. And because it's not a H, it's an R group, so an alkyl group. So it could be a methyl or an ethyl, just for examples. We call this an N-substituted amide because we've substituted the hydrogen that was on the nitrogen by an R group. So this is an N-substituted amide. And how we would name it would be, for example, if we had that this R group was equal to a methyl, what we would get would be N-methyl, and then you'd name the amide. So we've got 2 carbons, so this is ethanamide. So this would be the name if R was a methyl. Actually, for the N-substituted amide, it would be the N-substituted ethanamide, because we already know that we've got 2 carbons in the molecule, and so it must be ethanamide. And again, we started off with this ethanol chloride. So things to remember are that when we react an acyl chloride with water, we form a carboxylic acid. When we react the acyl chloride with an alcohol, we form an ester. When we react acyl chlorides with concentrated ammonia, we form amides. And when we react acyl chlorides with primary amines, we form N-substituted amides. And another really important thing to remember is the reaction with concentrated ammonia and how it reacts with 2 moles of ammonia and not just 1. So now we're going to have a look at some questions. For question 1, write an equation for the formation of methyl propanoate using a carboxylic acid and an alcohol. So remember back to when we were esters, and how we name esters is that we use the suffixes YL and O8. So this YL suffix is for the alcohol, and this O8 is for the acid. And so from this, we can work out which acid we used and which alcohol we used. So we can see that because it's methyl, we used methanol. And then because it's propanoate, that means we used propanoic acid. So we reacted these two together. And if you remember back to the equation, we had to use a H plus catalyst. And this would form the ester and water. So we would have this methyl propanoate. And water would be liberated. And so to write an equation for formation of methyl propanoate, we just need to do this, but with all the atoms. And so what we get is methanol is CH3OH because it only has 1 carbon. And then we add propanoic acid, so it has 3 carbons in the chain, and we have COOH on the end. And then again, we have this equilibrium when we add H plus catalyst and form this methyl propanoate. So we have 3 carbons and then double bond oxygen and then another carbon. And we also have water. Before I move on to question 2, feel free to click off the video and try it for yourself first. So for A, the repeating unit shown represents a polyester. Name this polymer and give the IUPAC name for the alcohol used to prepare this polyester. And so first, this is a condensation. Because in order to form this polymer, we have got rid of some water. And then for the IUPAC name for the alcohol, first we need to remember that to form a polyester, we need a diol and a dicarboxylic acid. And so we can split up this polyester that we've got into the alcohol bit and the carboxylic acid bit. So if I split it here, then this section here will be from the dicarboxylic acid. And this section here will be from the diol. And so it's the diol bit that we want. And so if I draw this out, it is HO and then CH2, 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 and then OH, because after we split up this C double bond OO bond, to get the dicarboxylic acid section and the diol section, we have to add the bits of water back on. And so we add these hydrogens back on. So this is the diol that we get. So then this diol would be propane 1,3-diol. because the two OH groups are on the first and the third carbons. And then for Bi, so the repeating unit shown represents a polyalkene copolymer, and this copolymer is made from two different alkene monomers. So first we need to name the type of polymerization occurring, and so the other type of polymerization is addition, and this is when we add up loads and loads of alkene monomers to form a long chain molecule, which is a polyalkene. And then for 2, draw the structure of each alkene monomer. So what we do here is we split it up, and then we get rid of these bonds here and form double bonds instead. And what we get is carbon double bonded to a carbon, and then we have hydrogen, another hydrogen, a fluorine, and another fluorine. So this is one of the monomers, and the second monomer would be carbon double bonded to a carbon, and then we have 2 fluorines on this carbon, a CF3 on this carbon, and a fluorine. And so these are 2 alkene monomers. And then for C, one of these 2 polymers cannot be broken down by hydrolysis. Identify the polymer and explain why hydrolysis of the compound does not occur. So we know that polyesters can be hydrolyzed, and so the polymer which can't be hydrolyzed is the addition, the polyalkene. So it looks like this. Well, we'll just put the addition polymerization product. So this is the polyalkene. And this is because it has unreactive carbon-carbon single bonds and also carbon-hydrogen bonds, as they are not polar. And so they don't attract attacking groups. Whereas if we look at the condensation polymerization, we always get this C double bond O bond, which is polar because you have a partially positive charge on the carbon and a partially negative charge on the oxygen, because there's such a big electronegativity difference between the carbon and the oxygen. And so this is attacked by some attacking groups, and so can be hydrolyzed.